Hi guys, assalamu alaikum. I hope you're all well and having a good day. So today we are back with the chromatography chapter, the last chapter of our chemistry unit for organic playlist. So if you guys have watched all the other videos, then welcome to the last video of this playlist where we will complete the whole unit for organic chemistry. And if you haven't watched them yet, then you can go through our previous videos from the playlist of unit for organic chemistry to complete and master unit for organic chemistry. Now, without wasting any more time, let's start the chromatography chapter. The first thing that we have to learn in the chromatography is the paper chromatography, something that we have learned in our IGCSE as well. This is something that we have learned in our IGCSE as well. So basically what we'll have to do in the chromatography. The first thing that we'll be doing in the chromatography or paper chromatography is um, we will take a mixture of the amino acid. Okay, there will be a mixture of amino acid, right? And we will just take one spot of that mixture of amino acid. Let's say there this is a mixture of the amino acid. Okay, this is a mixture of the amino acid, and out of this mixture of amino acid we will just take one spot and we will put that one spot in this place. Okay, in this place. Now you guys might ask me, why did we put it right here? Why not somewhere else? Because this is the baseline. We will always put the spot of the mixture of the amino acid in the baseline. Okay, then the baseline, so basically let's learn about it in more detail. So a spot of the mixture of the amino acid is placed on the baseline at the bottom of a square piece of chromatography paper, and the paper is left to dry. So basically this is a square piece of chromatography paper, of which at the bottom there is a baseline. At the bottom of this chromatography paper there is a baseline, and on that baseline we will put our spot of the amino acid mixture. Okay, and the second thing that we will have to do is we will let the paper to dry after putting the spot on the chromatography paper. The second thing that we will be doing is the paper is made into a cylinder and is fastened at the top with a paper clip. So basically we will make the paper's structure into a cylinder. Okay, we'll make, or we will actually fasten it into a cylinder, and after fastening it into a cylinder we will attach it with a paper clip and put it inside the beaker. Okay, inside the beaker. Let's say this was the actual chromatography paper and we have inserted it into a beaker using a paper clip. We will put it inside the beaker using a paper clip. There will be a paper clip which will be holding the paper inside the beaker. Okay, nothing else. Now in the third part they have said the chromatography paper is then placed in a beaker containing a solvent mixture, and the beaker is covered to prevent the solvent from evaporating. So basically the thing that I have said previously is that we will make the chromatography paper turn into the shape of a cylinder, and then we will put it into a beaker, and then we will we will cover the beaker so that the solvent inside the beaker doesn't evaporate out of the beaker. Okay, the beaker in which the chromatography paper will be put into, there will be a solvent from before. So basically there will be a solvent, and the beaker contains a solvent, and into that solvent we will um, place the cylinder with a paper clip. Okay, nothing else. Now we will wait for 20 minutes. After waiting for 20 minutes we'll remove the paper from the beaker, and then we will mark the solvent font position, because the solvent is into this line. The solvent is below. Something that we have to learn is this is the solvent. Okay, at the start the solvent is below this baseline. The solvent is below this baseline. After, as we have waited for 20 minutes, at that point the solvent will go up. The solvent will go up, and it will also carry some of the component of this spot of amino acid. It will carry some of the components of this spot of amino acid with itself. Okay, just like this one, it has carried some of the spots, or some of the components of the spot. While the solvent was moving up, it carried some of the components of these spot of amino acid. These are the components, and different components has gone up to different height. of the paper. Okay, and this is where the solvent font has reached. From this position to this position, it will reach right here. Okay, this is the position at which the solvent font will reach in these 20 minutes, where we will wait for the 20 minutes. Now these are the positions at which different components of the spot has reached. This is the height they have reached, right? So we'll have to make them visible, or we'll have to make them um, permanent, right? So to make them permanent and to make them visible, we will be using some materials. The thing is, the chromatographer paper will be then sprayed with neon hydrin and purple spots, so that these amino acids are seen, so that you can see this amino acid. To make these amino acids visible, we will use neon hydrin and purple spots. And at the sixth point, as I have said, to make it permanent, to make this component of spots permanent, or to preserve them, we will be spraying the paper, this whole paper, with a mixture of methanol, or this solution, or this dilute nitric acid, or we may expose it to concentrated ammonium fumes. You can also use pencil marks instead as well, to make them permanent. Okay, to make these spots permanent, you can also use pencil spots, so that we can understand how much they have actually gone up. Okay, with the solvent font, the solvent font has reached from this position to this position, right? But the component of the spot has reached in different positions, and depending upon the components. Now there is something called the retention factor. Then what is actually the retention factor? The retention factor value of each amino acid is calculated and then compared with the data book values for identification. Okay, so basically now let's look after the retention factor. There is a formula of retention factor. So basically there is a formula of the retention factor. The formula is done. Let's say the solvent was right here. Okay, let's say um, the solvent was right here at the start. The solvent was right here. So we will measure the distance covered by the solvent from its starting position till the end. Okay, we will cover this distance, this x centimeter, this distance traveled by the solvent, and then we will also measure the distance traveled by this component, or this component, as well as this component. Okay, so sorry. So to figure out the retention factor of, let's say, this A particle, what we will do is the retention factor of this A particle will be the distance traveled by this component divided by the distance covered by this solvent. For this B particle, we will use the distance covered by this particle divided by the distance covered by this solvent. And for this C particle is the distance covered by this C component divided by the distance covered by the solvent. So this is how we will be measuring or calculating the retention factor. So the retention factor, let's say this is x centimeter. So the retention factor of A will be A divided by x centimeter. Okay, we will measure them by this. So the retention factor of B will be B divided by x centimeter, and retention factor of C will be C divided by x centimeter. This is how we will be figuring out or calculating the retention factors. Okay, now let's understand them from the note. So what they have written: the retention factor value of each amino acid is calculated. We will calculate them and we will compare it with the data book values for identification. There are values of data book. Let's say the retention factor of A was, let's say, 12, and in the data book it is written that a component with retention factor of 12 is, let's say, methanol. So we'll be able to understand that yes, it is an methanol. Okay, so this is how we will be able to figure out actually which component it is. Okay, the amino acids are separated due to different interaction with the mobile phase, solvent, and stationary phase. So for different solvents, a particular amino acid will have different retention factor values. Okay, so let's say here the solvent that was used was water. So for water, this A particle has moved up to this point of the, okay, but if there was ethanol used rather than water, then this would have moved up to this. So the height the component of the spot reaches depends upon the solvent in which it has been done the paper chromatography. Okay, this is what they have written. Let's say this particle will move up to this point if water was used, But rather than water, if ethanol was used, then this particle would have reached this position. So basically, this is the difference, okay, of the solvent. So for different solvents, a particular amino acid will have different RF values. This is all about paper chromatography. Now let's move forward to thin layer chromatography. All right, guys, so now let's go through the thin layer chromatography. Now, the thin layer chromatography is exactly the same as paper chromatography. But in paper chromatography, we used to use a paper, right? But in thin layer chromatography, we will be using a glass or a plastic. Okay. The paper chromatography, we used to use a paper on which the spots were given, and then the solvent was moving up as well as the components of the spots were also moving up, right? But in thin layer chromatography, there will be a metal on which on the baseline some silica gels will be. So in the baseline, in this baseline, some of the silica gels will be put. Let's say I have put some silica gels on this baseline. Okay, I have put some silica gel on this baseline, and above or on this silica gel we will put the mixture, and there will be a solvent which will go up, and with this solvent the component of this mixture will also go up. This is what happens in thin layer chromatography. Okay, this is the main thing, and this silica gel doesn't move, they are immobilized. Okay, the silica gel or the amino acid, sorry, aluminum oxide is immobilized, they doesn't move. This is the main difference between paper chromatography and thin layer chromatography. All the other things are exactly the same thing. So I'm explaining the thin layer chromatography once again. So the thin layer chromatography is a technique that is used to separate and identify components in a mixture, just like paper chromatography. A thin layer chromatography plate is coated with a thin layer of silica gel. We have put thin layer silica gel right here, right? Which acts as the stationary phase. It is a stationary phase because it doesn't itself move. We have written it as immobilized. We can also say them as it is a stationary phase. The silica gel is a stationary phase. That means it is fixed and it doesn't move. The sample is spotted directly onto the silica gel. We'll put the sample directly onto this silica gel surface near the bottom of the plate. At the bottom of the plate, this is the bottom of the plate, right? Not on the baseline, actually it will be on the bottom of the plate. A solvent, which is known as a mobile phase because the solvent moves up, that's why we call them as mobile phase. um, the solvent moves up, okay, and it also carries the components depending on the polarity of that component, okay, and also the solubility in the solvent. Okay, let's say if a component is less polar, then um, they travel further as they are less attracted to the silica and more soluble. If let's say there are different components, component A and B, so component A will move right here and component B has moved right here. So why did component B move right here? Because the component B was in this spot, right? But the component B has moved further because it was less attracted to the silica gel and it moved with the solvent. But component A moved less because it was more attracted to the silica gel and the solvent couldn't take it as further as he would have liked. Okay, these are the couple of things that you guys will have to understand, which is not in the note. So basically these are some basic things, though it is written in column chromatography or high performance liquid chromatography, don't worry, but the concept is the same. If someone is more attracted to the silica gel, it will travel further distance, sorry, travel less distance. But if it is it has a weaker attraction or weaker interaction with the silica gel, then it will move further because it is easier to make the components apart from the silica gel by the solvent if the attraction between the silica gel and the component is less. So this is the main thing. Hopefully you guys have understood this part. If you didn't, then you guys can comment down below. I will try to help you guys as much as possible on this particular thing. Now let's move forward to the column chromatography. Column chromatography is also another chromatography which uses the same principle as the thin layer chromatography. Okay, where the stationary phase is alumina or silica. So basically we will pack this whole tube with alumina or silica. Okay, let's say there will be a lot of alumina and silica right here. There will be a lot of alumina and silica right here. They are, let's say, they are particles. Okay, we will pack the whole funnel or this let's say this beaker or this funnel, not a beaker actually, we will actually um, put this container with a lot of silica or alumina, okay, which are packed into this container using a burette, in a burette, okay, and then we will soak them in a solvent. We will soak these particles in a solvent. Okay, they are stationary phase. That means these particles are not gonna move. Okay, the particles are not gonna move. The particles are not gonna move, and they will be soaked in a solvent. So basically, we will put the solvent from the up. Okay, and after, let's say this is a container. In this container I have put a lot of particles, and these particles are alumina or silica, so the particles will not move. And after putting the particles, then I will put some solvents into it. So basically I'm soaking the particles into a solvent. Then what I will be doing is I will put the mixture of amino acids or the mixture of any particle of which we're actually carrying the column chromatography. Okay, the mixture, actually the you can say the reaction mixture as well. The thing, no, we are not actually reacting it, we're actually doing column chromatography. So we can say that chromatography mixture or something like that. So the mixture will be placed on top of the stationary phase. So let's say we'll put the mixture right here. Okay, we'll put the mixture right here on top of the stationary phase, or we can also say on top of the particles, just like here they have put the they have put the mixture on top of the stationary phase, and then a lot more solvents will be put from the top. Okay, added on top. Then we will open this funnel. So when we will open the tap, when we'll open the tap, at that time the solvents will start flowing down, right? The solvents will start flowing down because the solvents are liquided, they will start falling down. So when they will be actually falling down, and we are also putting solvent from the top. There basically there is particles right here, and on top of particle there is the mixture, and on top of the mixture we are putting the solvent. So the solvent will be falling down this container, right? The falling down this container. So when the solvent will be falling down the container, it will be carrying the mixture with it, right? So the mixture will get um, away from each other. So the mixture are broken down into two components. Okay, so the components will start falling. The components will start falling. So when the tap is opened, the solvent drips through the top, and the components of the mixture begin to move down the tube and separate. More solvent is added at the top. When you add more solvent, and eventually one component, yellow in this example, the yellow component falls at first, leaves the column, and can be calculated in a container. If the experiment is continued, the blue component can be collected in the same way. This is what actually means as the this is what actually means as the column chromatography. Okay, the column chromatography. So when the solvent was falling, the more polar the mixture is, the more attracted it gets to the solvent. So when it gets more attracted to the solvent, it gets get out of the container at first. Let's say here the blue one was more polar, so it get more attracted to the water, and it started falling more quickly than the blue one. So the yellow one has more attraction, or more, it was more attracted to the solvent. That's why it was falling way more quickly than the blue one. So this is what actually is happening in the column chromatography. Now let's go through the high performance liquid chromatography. Now high performance liquid chromatography is exactly the same as column chromatography, but there are some exceptions because high performance liquid chromatography is a bit more modernistic. Okay, it is a more updated version of the column chromatography. High performance liquid chromatography is a refinement of the column chromatography. So how does high performance liquid chromatography differ from the normal chromatography or column chromatography? The difference is that in column chromatography we have seen that the solvents were falling just like this, and the solvents were falling by the force of gravity, right? It was falling by the force of gravity. But here the solvent will be forced to fall through the metal tube under high pressure. We will be providing high pressure so that it falls as more quickly as possible, or we will force them to fall as much as possible. So we will not wait for the gravity to make them fall down. We will put pressure on them so that it gets down. Okay, and the second difference is the particle size of the stationary phase is much smaller, which leads to better separation of the components. Let's say in the column chromatography, in the column chromatography, the stationary phase particles was this big. Okay, but in high performance liquid chromatography, the size of the particles of stationary phase is way smaller than this. So what it actually does is, if the particles are smaller, then while the mixtures are falling, they face more what do you say, they face more restrictions, or they face more prevention from falling, so it is more difficult for them to fall. So we can figure out how much stronger one mixture is from the another one, or how better one mixture is from another one. Okay, so we can get out more clearer picture of the strength of the mixtures. This is how we can figure out the separation of the components. The components get separated. Okay, the difference is more visible. If I make you guys understand using an analogy, okay, if I make you guys understand an analogy, let's say um, in high performance liquid chromatography, the column is packed with very small particles, right? I have shown that to you guys, which gives better separation of mixture of components. Why? Because smaller particles provide more surface area for interaction. As it is providing more surface area, okay, it provides more surface area, and it also create narrower pathways for the molecules to travel. Okay, let's say here, when the particles are bigger, it has got a bigger pathway to travel, but when the particles are smaller, then the pathway is very small, so it becomes a narrower pathway for the particles to particles to go through. So for an analogy, let's say if the trees are very big and far apart, the two trees are very big and they are far apart. Okay, so let's say you and your friend are um, actually running in a forest. So basically, if there are more space between the two bigger trees, both of you guys can easily travel through it. Okay, but if the trees are very small and they're very closely packed together, so it will take you guys to know how to get out of it, right? It will bring out the best out of you guys. It will take out your skill, your knowledge, your IQ level to get out of this forest. So basically here, maybe one of you guys will be able to get out of these smaller, closely packed trees. So here we can separate the components in the better possible way. This is one analogy that can be used. Okay, but let's say if the forest has many small closely packed trees, the runners face more obstacles and must carefully navigate the path. Even small differences in their speed or reaction cause them to exit at noticeably different times. Similarly, in HPLC, components with even slight difference in how they interact with the stationary phase will travel at different speed and be separated more quickly. Okay, let's say your friend is a little has a greater weight than you, so you will be traveling more quickly between these small and narrower trees, but your friend will face more difficulties to travel through these narrow spaces. This will make the separation. Otherwise, if there was a very bigger space, then you both could have traveled in the same speed. So this is how we'll be able to separate the components between you and your friend who has a greater speed. This is how we'll be able to separate them. The next point is a sample is injected into the column. In the column chromatography, we just put the sample right here. But in high performance liquid chromatography, we will put the sample into the container using, we will actually inject them into the column. Okay. So the next point is the whole process is automated and the results are quickly available on a computer display. So in a computer display, the results are quickly um, automated and are displayed. Okay. Now we have learned about the retention factor previously. Right? We have learned about the retention factor. Now we will go through the retention time. Now, all right. So now let's go through the retention time. So what is actually retention time? We have learned about the retention factor, right, in paper chromatography. But here we will be going through a retention time. So the retention time of a component is the time taken from the injection to detection. From injection to detection means, let's say you have injected the particle, you have injected the mixture, and the time started as soon as you injected the you have injected the mixture, and at the time it is detected in the detector. Okay, when it will just start falling at the very second, at the very first second when it will start falling. So basically this is what the retention time, at the very start when you will put the mixture, to at the very start, very first second at which the detector will detect the particle or the mixture or the component of mixture falling down. This is what the retention time is. Now the detention time is the time taken from injection to detection, injected to the detected from the detector. Now this retention time actually depends upon a couple of things. The first thing is the nature of the solvent. Okay, the nature of the solvent. Let's say the solvent is very strong. If it is very strong, it will take the mixture with itself and it will make the mixture fall as quickly as possible. So let's say for this yellow one, okay, well then let's say if the mixture was very strong, then this yellow one would have fallen in a much smaller time. Let's say this yellow one took 5 seconds to fall from this height, but if the solvent was much more stronger, then it would have taken 3 seconds. So the stronger the solvent is, the lesser is the retention time. From the injection to the detection, it takes lesser time. The pressure used, if you use more pressure to the solvent falling, then the solvent will fall quickly, as well as it will take the component of mixture with itself quickly, and the retention time will be smaller as well. Now the temperature inside the column, if the temperature inside the column is very high, the viscosity will be less. The viscosity is the opposite force acting, right? Viscosity acts in this direction and the particle falls in this direction. So if the viscosity is less, then the particle will fall as quickly as possible, so the retention time will be smaller as well. So basically these are the ways in which the retention time depends upon. Now let's go through the gas chromatography. Okay, what is actually the gas chromatography? So basically gas chromatography is another refinement of column chromatography. The main differences of gas chromatography is that there will be a meter. There will be a metal which will be several meters long and it will be coiled to save space. If I show you the picture, this is actually the metal figure. Okay, this is actually the metal figure. Let's take it in onto the last onto that page and paste it right here to show you guys about this in a much more detailed way. Now let's go through this part. So basically it is coiled right here to save space. If it is coiled to save space. Now the stationary phase in this gas chromatography is a solid or liquid coated on the inside of the tube. So in this tube there will be a solid. Let's say this is a solid that will be put in this coiled tube. Okay, there will be a solid or a liquid that will be put in this coiled tube. The mobile phase will be an inert carrier gas of a nitrogen or helium. The mobile phase will move through this coil. The mobile phase will move through this coil, and there will be a solid or liquid that will be our stationary phase. This stationary phase will not move. Actually, the gas will move. Okay, and the sample of mixture will be injected into the column. Let's say the injection port here. the sample will be injected. Okay, the sample will be injected right here. You guys can see an example right here. This is an example that this is the samples, and the samples are moving and they're getting separated. The samples are getting separated. Okay, the gas is moving, and while the gas is moving, the gas is also carrying the mixture. And when the gas is carrying the mixture, some of the mixture, all of the mixtures are separated. Okay, the components passing through the columns are detected. The whole process is automated and the results are quickly available on a computer display. Just like high performance liquid chromatography, gas chromatography is also automated, and the results will be displayed on the computer. Okay, so basically let's go through this part right now. After the sample is ejected, the components vaporize and move through the coil tube. The particles will move through the components of the sample will be vaporized at first, and then it will move through the coiled tube with the carrier gas. They move at different speed. Let's say this one has different speed, this one at different speed, and this one at different speed, depending on how strongly they're attracted to the stationary phase. There was a stationary phase right here, right? There was a stationary phase right here. Let's say this was the stationary phase. If a particle, let's say this particle is moving at the lowest speed, right, and this one is moving at the highest speed, so this particle was very strongly attracted with the stationary phase, which was right here. So it was more strongly attracted with the stationary phase, that's why it is moving at the lowest speed. And this one was less strongly attracted with the stationary phase, that's why it is moving at the fastest speed, and it is above this all of them. Okay, it is ahead of all of them. Those with weaker reaction move quickly and have shorter retention time. So it will have shorter retention time. From the injection to the detection, it takes lesser amount of time. Now let's understand about the limitations of HPLC and GC. HPLC means high performance liquid chromatography, and GC means gas chromatography. There are some actually limitations of these two things. These two things are actually used in terms of forensic evidence. If a court asks us for the forensic evidence, we use this high performance liquid chromatography and gas chromatography. It is also used in detecting banned drugs in sportsmen, whether a sportsman has doped or not, or if it has taken, let's say, testosterone booster or testosterone supplement or not. And also for women, and also for race horses as well. For detecting this type of things, high performance liquid chromatography and gas chromatography are used. Now there are some limitations. Why there are limitations? Because there is a difficulty of controlling all of the variables, such as the solvent. You need a very strong solvent, so it is difficult to provide a very strong solvent, a very high pressure as well, and that maintaining the temperature is also difficult. And let's say there are a couple of substances that have the same retention times. So maintaining all of these things altogether is a very difficult is a very difficult job to do. That's why this HPLC and GC is a difficult procedure, and they have some limitations as well. These are the limitations, that you cannot always maintain all of them. Okay. Now, they are also used in other areas, including analysis of pollutants in the environment, detecting explosive in airport baggage, and in space probes on another planets. So they have a very good usage as well, but it is difficult to maintain all of these criterias. Okay, so it is difficult to maintain all of these things, but they have very good usages as well. So memorize the limitations of HPLC and GC, and also how they are actually used. Now, as we have understood that they do not give positive results always, not positive results, actually they do not give accurate results always. Okay, we cannot always say that GC and HPLC are giving the accurate results. So that's why we always use mass spectrometer as well. We use HPLC and GC with mass spectrometry, because because the result of HPLC and GC solely is not reliable, because they don't give accurate results always. That's why we always use mass spectrometry with them. Along with them, we combine HPLC and GC with mass spectrometry, and they can also be said as HPLC-MS and GC-MS, gas chromatography, mass spectrometry. So how the mass spectrometry is actually used. So first of all, it is exactly the same thing. First, the mixture is injected into a gas chromatograph, like the gas chromatography, where a sample was injected into the gas chromatography, right? Now each component has a different retention time, so matches are a different time, right? All of these three particles had different retention times. That's why they are in different phase and they are in different part. One is ahead of the other one, right? Everyone is at different places. That's why, and they all three of them will have different retention time. Let's say this one will take um, let's say this one will take 3 seconds, whereas this one will take 5 seconds and this one will take 8 seconds to be detected, right? Now the third point says one at a time each component enters the mass spectrometer, right? This one enters the mass spectrometer first, then this one, and then this one. So all of them are entering at a time, after one another, right? One enters after the other. Now the fourth point is component C has its spectrum displayed. Let's say this component C is taken into gas chromatograph, and in the gas chromatograph there is this absorption line that we have learned in our previous NMR spectroscopy as well, right? And this NMR and then this chromatograph is something that will show these peaks, okay? And then we will pass them through the mass spectrometer. And what this mass spectrometer will do is this mass spectrometer will show their mass spectrum according to their mass to charge ratio and their abundance. And according to that, let's say the mass spectrum of component C is 109. So what we will do is we will compare this 109 mass to charge ratio and abundance, okay, in the data booklet. We will have a data booklet. If the data booklet shows that a component which is 109 value is, let's say, a helium, so we can understand that yes, we have got a helium as component C. So this is how we will be able to compare the mass spectrometry with the data booklet. Now in the fifth point, they have said the mass charge values and relative abundance of components are compared with a database of known substances. We know the database of known substances. Let's say this component C has 109 value. So if it has a value of if it has a mass to charge value of 109, then we will go to our known database and we will look after, let's say in the known database we have written 110 is for nitrogen and 109 is for helium. So as we have got a value of 109, we can understand that compound C was a helium. So when a match is found, component C has been positively identified. So we have identified our component C. So basically this is how chromatography is all about. So now we are completely done with the chromatography chapter as well, and we are completely done with the whole chemistry unit for organic part. Hopefully you guys have enjoyed this whole playlist. If you guys haven't watched the whole playlist yet, then please go and watch the videos because it will help you guys to ameliorate your preparation. Now I hope you guys have enjoyed the syllabus completion of the unit 4 organic with me. If you want to complete the unit 5 organic with me, or if you want to solve more question papers with me, do join our high impact crash course and question papers marathon course. These are the two courses that we always launch before every exam session. So if you are a May 25 candidates, you can join our question papers marathon course to ameliorate your preparation. And if you have much time left, then you can join our high impact crash course for, let's say, October 25, Jan 26 or May 26 session. So before 2 months of every exam session, we launch question papers marathon course, and before 4 to 5 months we launch the high impact crash course. No matter how near your exam is, whether it is 15 days or 20 days left, feel free to message our Facebook page Exam Essentials, or WhatsApp us at our WhatsApp number given in the description box. The course details is also in the description box. Feel free to message us. We will help you guys to ameliorate your preparation because we have very good recorded question paper solving videos which are unlisted only for our registered student. So feel free to message us and get those things for yourself, because we will get the chance to do our live classes as well as the recorded question paper solving videos or recorded videos of the syllabus. So why to waste time? Join our high impact crash course or question papers marathon course to ameliorate your preparation. And we have got very good um, um, worksheets as well for maths, physics, chemistry, biology, business, accounting, law, politics, and each and every subjects, including economics as well for both O levels and A levels. So don't waste your time. Join Exam Essentials.